October 19th, 2017. The Pan-STARRS telescope at Haleakala Observatory sits beneath Hawaiian stars, its mirrors collecting ancient light. Robert Varick examines the data from this automated survey, expecting another ordinary asteroid, another fragment of our own solar system's construction debris. The object appears as a faint point of light, magnitude 19.540,000 times dimmer than what human eyes can perceive. Its position shifts between images taken 45 minutes apart. Standard procedure, routine observation, except the mathematics refuse to behave. The velocity calculations emerge wrong, not slightly wrong, fundamentally wrong. The object moves at 26 kilometers per second relative to the Sun, far too fast for any gravitational capture, too swift for any elliptical orbit that would bring it back. The computers run their calculations again. The trajectory curves through space like nothing in 4 billion years of solar system history. This visitor carries the momentum of deep space, the signature of stars humanity has never named. The observatory's automated systems flag the anomaly. Other telescopes pivot on their mounts, great eyes turning toward coordinates that shouldn't matter. The Canada-France-Hawaii telescope confirms the impossible trajectory. The European Southern Observatory traces the same hyperbolic path. Each measurement adds certainty to an uncomfortable truth. This object falls toward our Sun from interstellar space, untethered to our star's gravity, uncommitted to staying. At first, they assume Comet. Comets arrive from the Oort cloud with tremendous speed, ice-laden wanderers from the solar system's frozen edges. But this object's path traces back to no cloud, no reservoir of ancient ice. Its trajectory extends backward through empty space, through the void between stars, through distances measured in light years rather than astronomical units. The software designed to calculate orbits returns error messages, mathematical impossibilities. The object ignores the closed loops and elegant ellipses that define our local neighborhood. The Discovery team checks for errors in parallax, in timing, in coordinate systems. Perhaps someone misaligned the telescope. Perhaps cosmic rays struck the detector. Perhaps anything except what the data insists a visitor from another star system now passes through our own, the first ever confirmed, moving too fast to ever return. Only took 4.5 billion years for humanity to develop eyes capable of seeing such a thing, a cosmic irony as dry as lunar dust. Within hours, observatories worldwide receive urgent requests for telescope time. The object races sunward at speeds that make every hour precious. Whatever this is, wherever it originated, it won't linger for extensive study. The universe delivers its first confirmed messenger from another star, and humanity scrambles to decode its meaning before physics carries it away forever. The Pan-STARRS data spreads through secure networks, through encrypted channels, through communities of scientists accustomed to decades-long investigations, suddenly confronting a deadline measured in weeks. They need a name for this impossibility. The International Astronomical Union, keeper of cosmic nomenclature, faces a classification crisis. No existing category fits. Not asteroid, not comet, not planet. Something new requires something new. They create a designation never used before. Why? Where I stands for interstellar. The first of its kind. The beginning of a new catalogue that might take centuries to fill, or might never receive another entry. The name Oumuamua emerges from Hawaiian, chosen to honour the observatory that spotted humanity's first confirmed interstellar visitor. It means scout, or messenger, or reaching out for. The telescope that found it sits on sacred ground, on Mauna Kea, where earth touches sky. How appropriate that humanity's first glimpse of an object from another star should come from a place where ancient Polynesian navigators once studied the stars for their own voyages across vast waters. Different ocean, same navigation by light. The mathematics of arrival tell a story written in velocity and angle. Every object bound to our Sun follows predictable paths ellipses for planets. stretched ovals for comets, slow circles for distant Kuiper belt objects. These paths close, they return, they belong. But Oumuamua's trajectory opens into infinity, a hyperbolic arc that touches our solar system once before extending into forever. The sun's gravity bends its path but cannot claim it. Like a stone skipping across a pond surface, it deflects rather than settles. Astronomers trace the object's path backward through time and space. The calculations require adjusting for the sun's own movement through the galaxy, for the gentle spiral of our local stellar neighbourhood, for the gravitational influences of planets past and stars nearby. The trajectory extends through interstellar vacuum, through the empty spaces between stars where matter spreads thinner than the best vacuums humanity can create. 1 atom per cubic centimetre, sometimes less. Oumuamua travelled through this nothing for times measured in geological epochs. The model suggests 40,000 years since it last approached any star as closely as it now approaches ours. 40,000 years of darkness, of cold approaching absolute zero, of cosmic ray bombardment with no atmosphere or magnetic field for protection. While humanity painted caves and carved bone, this object drifted through vacuum. While civilizations rose and collapsed, it maintained its course. While languages evolved and disappeared, it moved in straight lines between the stars, patient as geology. Its incoming velocity relative to the local standard of rest, the average motion of stars in our neighbourhood measures unusually slow. Most stars move at 20 or 30 kilometers per second relative to this cosmic benchmark. Oumuamua arrived at merely 11. This suggests an old object, something that has circulated through the galaxy long enough for gravitational interactions to calm its motion. Or perhaps it emerged from a particularly quiet stellar nursery, a place where stars form with minimal turbulence. The velocity carries information, but astronomers struggle to decode its meaning. The direction matters too. Oumuamua approaches from the constellation Lyra, from coordinates near the star Vega. Though Vega itself sits too far away to be the source, the object passed that star's position 200,000 years ago. When Vega occupied different coordinates entirely, stars drift through space like slow fireflies, their positions shifting over cosmic time. Tracing Oumuamua's origin requires accounting for this stellar choreography, this slow dance of suns that makes every trajectory a four-dimensional puzzle. Initial estimates suggest an origin within a few dozen light years, perhaps from one of the sun's neighbouring stars. Ross 619 passes through the calculations, so does HD 2249, but none align perfectly. The object might have wandered for millions of years, its initial ejection velocity modified by countless gentle gravitational tugs from stars passed in darkness. Each stellar encounter would bend its path slightly, would add or subtract velocity, would erase information about its true origin. The galaxy mix's trajectories like shuffling cards only took a few million years to scramble the evidence beyond recovery. Scientists calculate the rate of such visitations. If Oumuamua represents a typical example, if interstellar space contains vast populations of ejected planetesimals, then thousands pass through our solar system each year. Most remain invisible, too small or too distant for detection. They arrive and depart unnoticed, cosmic ghosts that haunt the spaces between planets. Humanity's telescopes caught this one by chance, by the coincidence of position and timing and sufficient brightness. How many others passed while humanity looked elsewhere? The discovery reshapes estimates of interstellar debris density. Previous calculations suggested sparse distributions, occasional objects separated by vast emptiness. But Oumuamua's detection implies abundance, perhaps one object per cubic astronomical unit throughout the galaxy. Multiply that density by the galaxy's volume and the numbers become staggering. Quadrillions of objects drifting between stars, each carrying information about its home system, each a message in a bottle thrown into the cosmic ocean. The object's interstellar nature explains certain peculiarities. Its orbit shows no evidence of non-gravitational forces from outgassing, the jet-like emissions that define comets. 40,000 years between stars would sublimate away most volatile ices, would leave only the most refractory materials. Or perhaps it never contained significant ice. Perhaps it formed in conditions unlike anything in our solar system. The possibilities multiply faster than observations can constrain them. By the time astronomers fully grasp what they're seeing, Oumuamua has already passed its closest approach to Earth. It came within 24 million kilometers, about 60 times the Earth-Moon distance 2 weeks before discovery. Humanity's first confirmed interstellar visitor arrived unannounced and nearly departed unnoticed. The universe doesn't schedule its revelations around human preparedness. It simply delivers mysteries when physics demands, indifferent to whether anyone watches. The light arrives in pulses every 7.3 hours. Oumuamua brightens by a factor of 10, then fades again into near invisibility. No asteroid in human catalogues behaves this way. No comet shows such extreme variation. The brightness changes suggest something unprecedented, an object with dimensions that challenge understanding, proportions that shouldn't exist, geometry that defies 4 billion years of solar system precedent. The mathematics of reflected sunlight reveal shape without seeing shape. When objects tumble through space, their brightness varies as different surface areas face the sun. A sphere shows no variation. A slightly elongated object might vary by 20 or 30%. Oumuamua varies by 1000%. The calculations converge on an uncomfortable conclusion. This object stretches 6 to 10 times longer than its width, perhaps 400 meters long but only 40 meters wide. A cosmic needle. A spear thrown between stars. Astronomers run their models again, seeking errors. Perhaps multiple objects travel together, creating the illusion of brightness variation. Perhaps the surface reflects light irregularly, patches of bright and dark material rotating into view. But the light curve remains stubbornly consistent, rotation after rotation. The same extreme brightening and dimming every 7.34 hours. The simplest explanation demands accepting the impossible, an object shaped like nothing nature typically creates. In our solar system, collisions and gravity conspire to round things out. Asteroids begin irregular but gradually approach spherical forms as impacts chip away protruding edges. Comets fragment into chunks but rarely into needles. The physics of accumulation favours compact shapes, not extreme elongation. Yet Oumuamua ignores these preferences. It tumbles through space like a thrown stick, rotating not around one axis but complexly, chaotically, in what astronomers call a non-principal axis rotation state. Like a poorly thrown football, it wobbles as it spins. This tumbling carries information about violence. Stable objects rotate around their shortest axis, the configuration that minimizes energy. Oumuamua's complex rotation suggests recent disruption, recent meaning within the last billion years, a heartbeat in cosmic time. Perhaps tidal forces from a close stellar passage set it tumbling. Perhaps a collision in its home system knocked it into this unstable state. Perhaps the same event that ejected it into interstellar space also left it spinning chaotically, a cosmic casualty carrying evidence of ancient catastrophe. The shape poses problems for natural formation theories. Planets and asteroids form through accretion, particles sticking together in protoplanetary disks. This process builds roughly spherical objects, or at least objects without extreme aspect ratios. To create something as elongated as Oumuamua requires special circumstances. Perhaps it represents a fragment of a larger body, sheared off during a grazing impact. Perhaps tidal forces stretched it during formation near a massive planet. Perhaps processes unknown to our solar system operate elsewhere. Only took discovering one interstellar object to reveal how much we assumed about universal formation mechanisms. Some scientists propose a contact binary, two separate objects that gently collided and stuck together. This might explain the elongation without requiring exotic formation processes. but the light curve shows no evidence of different materials or densities that such a merger would create. The brightness varies smoothly, suggesting uniform composition throughout. Whatever Oumuamua is, it appears to be one thing, not two things pretending to be one. The colour measurements add another puzzle. Oumuamua reflects red light slightly better than blue, similar to organic-rich asteroids in our outer solar system, but not quite the same. The specific shade doesn't match any taxonomic class in asteroid catalogues. 40,000 years of cosmic ray bombardment would redden any surface, would cook organic molecules into complex polymers, would create a patina unlike anything in our neighbourhood. The object wears its interstellar journey on its surface, painted in wavelengths that speak of deep time and hard radiation. Artists struggle to depict what no telescope actually resolved. Every image shown to the public represents artistic interpretation based on brightness mathematics. The object remained a point of light throughout its visit, never more than a pixel in humanity's best instruments. Yet the light curve demands accepting its needle-like form. Science sometimes requires believing what cannot be directly seen, trusting mathematics more than intuition. Oumuamua exists in human consciousness as pure inference, a shape built from photons and calculus. The tumbling continues as it departs, indifferent to human puzzlement. 7.34 hours, bright to dim to bright again. A lighthouse beacon growing fainter with distance. Each rotation carries it roughly 750,000 kilometers farther from Earth. The brightness variations that revealed its shape also mark its departure, each pulse slightly dimmer than the last, a cosmic metronome keeping time as the universe reclaims its messenger. September 9th, 2017. Oumuamua passes within 38 million kilometers of the Sun, closer than Mercury's orbit, where temperatures exceed 400 degrees Celsius. At this distance, ice sublimates violently. Comets grow spectacular tails. Volatile materials boil away into space, creating the streaming clouds of gas and dust that define these ancient wanderers. Every comet that approaches our Sun announces itself through outgassing, through the spectacular transformation of solid to vapour. Oumuamua remains silent. The telescopes search for signs of sublimation. Spectrographs analyse light for emission lines of water, carbon monoxide, carbon dioxide, the usual suspects that create cometary Comet. The Hubble Space Telescope dedicates precious observation time, its instruments capable of detecting even minimal outgassing. The Spitzer Space Telescope searches in infrared, where warm dust would glow against cosmic darkness. Nothing, no coma, no tail, no evidence of volatile materials responding to solar heat. The object passes through our inner solar system as inert as granite. This absence tells its own story. Comets from our Oort cloud contain pristine ice preserved since the solar system's formation. When solar radiation heats them, they respond dramatically, sometimes fragmenting from thermal stress, always streaming material into space. But Oumuamua shows no such drama. Either it never contained significant ice, or 40,000 years between stars sublimated away every volatile molecule, leaving only refractory materials that ignore the sun's warmth. Scientists calculate what should happen if Oumuamua contained even trace amounts of water ice. At its perihelion distance, a sublimation should produce detectable hydroxyl emissions. The equations predict specific wavelengths, specific intensities, specific distributions around the object. The observations show none of these signatures. Upper limits emerge from non-detection less than 1 kilogram per second of water production, hundreds of times lower than typical comets at similar distances. The object guards its composition jealously. The mystery deepens because something must have ejected Oumuamua from its original system. Planetary encounters can scatter objects into interstellar space, but this requires specific conditions. The object needs sufficient velocity to escape its star's gravity, but not so much that it would travel faster through interstellar space. The slow approach velocity suggests a gentle ejection, perhaps from the outer regions of its home system where escape velocities are lower. but outer system objects typically contain ice. The paradox resists easy resolution. Alternative compositions emerge from theoretical necessity. Perhaps Oumuamua consists of materials uncommon in our solar system, organic polymers created by cosmic rays, metallic hydrogen formed under extreme pressure, carbon chains linked in configurations unknown to terrestrial chemistry. Each hypothesis attempts to explain the observational constraint's elongated shape. No outgassing, slight reddish colour, complex tumbling. None fully succeed. The object refuses to fit categories derived from local experience. Only took one interstellar visitor to reveal our provincial assumptions about cosmic chemistry. Some propose that Oumuamua represents a desiccated comet, its volatile inventory exhausted through multiple close stellar passages. Perhaps it encountered other stars during its interstellar journey. Each approach sublimating away more ice until only rocky matrix remained. But the calculations struggle with this scenario. Complete desiccation requires specific conditions, repeated heating events that seem statistically unlikely. The galaxy is vast and stars are sparse. Most objects ejected into interstellar space should never again approach stellar warmth. The lack of dust proves equally puzzling. Even rocky asteroids shed particles when heated, microscopic fragments liberated by thermal expansion and contraction. Sensitive instruments should detect this dust through its infrared glow or forward-scattered sunlight. But Oumuamua produces no detectable dust trail, no microscopic debris marking its passage. The object maintains perfect integrity despite temperature swings that would fracture most materials. Perhaps its surface formed a protective crust during eons of cosmic ray bombardment, a rind that resists thermal degradation. Laboratory experiments attempt to recreate interstellar conditions. Scientists bombard ice samples with radiation doses equivalent to millions of years between stars. They cycle temperatures from near absolute zero to solar heating. They search for material combinations that could survive such treatment while maintaining structural integrity. The experiments produce interesting chemistry, complex organics, polymerized surfaces, unusual crystal structures, but nothing quite matching Oumuamua's peculiar properties. The sun's gravity bends Oumuamua's path by 60 degrees, a gravitational slingshot that redirects it toward the constellation Pegasus. As it climbs away from perihelion, still no tail appears. The object that arrived incognito departs equally mysteriously, offering no chemical signatures, no spectroscopic fingerprints, no compositional clues. It passes through the solar system's warmest regions as unchanged as a stone through water, leaving only gravitational evidence of its passage. The universe's first confirmed messenger maintains perfect operational security about its nature and origin. June 27th, 2018. The European Space Agency releases new trajectory data from ground-based telescopes and the Hubble Space Telescope. 34 observations over 200 days track Oumuamua's departure with unprecedented precision. The measurements should follow a perfect hyperbola, the path defined purely by gravity. They don't. The object accelerates away from the Sun faster than gravity alone permits, not dramatically just 30 micrometers per second squared, but undeniably. Something pushes Oumuamua besides the Sun's gravitational field. The Discovery team checks their calculations repeatedly. Perhaps they miscalculated solar radiation pressure, the gentle push of photons against the object's surface. Perhaps they overlooked gravitational perturbations from planets or asteroids. Perhaps measurement errors accumulated into apparent acceleration. But the data remains consistent across multiple telescopes, multiple nights, multiple analysis techniques. Oumuamua experiences a small but persistent force directed away from the Sun, decreasing with distance as solar radiation decreases. The pattern matches cometary acceleration perfectly, except this object shows no cometary activity. When comets outgas, the escaping vapor acts like tiny rocket engines, accelerating the nucleus in the opposite direction. Astronomers understand this process well, can predict acceleration based on observed gas production, can model how non-gravitational forces vary with solar distance. Oumuamua shows the acceleration without the outgassing. It behaves like a comet while appearing completely inert. The universe presents a puzzle wrapped in impossibility, delivered at 26 kilometers per second. Scientists calculate the minimum outgassing required to produce the observed acceleration. For an object of Oumuamua's estimated mass roughly 10 million metric tons, the mathematics demand specific gas production rates. But achieving these rates with undetectable outgassing requires unusual circumstances. Perhaps jets emerge only from the object's ends, hidden when viewed from Earth. Perhaps the gas consists of molecules transparent to our instruments. Perhaps dust particles too large to scatter light efficiently carry away momentum. Each explanation requires increasingly special conditions. The acceleration rules out certain compositions. Pure rock or metal would be too massive for such subtle forces to accelerate detectably. The object must have relatively low density, perhaps highly porous, perhaps hollow, perhaps constructed of materials lighter than typical asteroids. But low-density objects face their own challenges surviving interstellar journeys. Cosmic rays would erode fragile structures. Microscopic impacts would gradually destroy porosity. The object needs to be simultaneously lightweight and durable. Only took discovering non-gravitational acceleration to add another seemingly impossible requirement. One hypothesis suggests that Oumuamua consists of molecular hydrogen ice, frozen at temperatures below 14 Kelvin. Such material would sublimate invisibly, producing acceleration without detectable emissions. Hydrogen ice could form in the coldest regions of giant molecular clouds, the stellar nurseries where stars are born. But hydrogen ice faces stability problems. It requires formation conditions unknown in our solar system and preservation through processes that should destroy such fragile material. The hypothesis solves one mystery by creating others. Another proposal invokes nitrogen ice, like the frozen plains on Pluto's surface. Pure nitrogen would sublimate at solar distances where water ice remains stable, potentially explaining the lack of visible outgassing near Earth. A chunk of nitrogen ice knocked free from an exo-Pluto might survive interstellar travel while retaining enough volatiles to produce the observed acceleration. But the mass estimates become problematic. The object would need to be almost pure nitrogen, with densities and albedos precisely tuned to match observations. Some scientists explore more exotic possibilities. Perhaps Oumuamua represents technology rather than nature, its acceleration produced by light sails or directed propulsion. The hypothesis emerges not from desire, but from elimination when natural explanations grow increasingly contrived. Even unlikely possibilities deserve consideration. But extraordinary claims require extraordinary evidence, and Oumuamua provides only ordinary puzzles. The acceleration fits patterns seen in solar system comets, just without the expected visible cause. The acceleration continues to decrease with distance, following an inverse square law consistent with solar radiation as the ultimate power source. Whether through sublimation or radiation pressure or unknown mechanisms, the Sun drives this motion. By the time Oumuamua passes Jupiter's orbit, the non-gravitational acceleration drops below measurable limits. The object returns to purely ballistic motion, coasting on momentum earned during its solar passage. Astronomers revisit their earlier observations, searching for missed clues about composition and structure. Perhaps the acceleration was always present, but too subtle to detect until sufficient data accumulated. Perhaps the object changed during solar approach, some dormant process activated by heating. Perhaps humanity simply lacks the conceptual framework to understand what seems paradoxical. The universe has no obligation to conform to human expectations derived from one planetary system's limited sample of objects. The spectra arrive fragmented and inconclusive. Each telescope that observes Oumuamua captures reflected sunlight, photons that bounced off its surface carrying information about composition. But the object remains faint, the signal barely distinguished from noise, the chemical fingerprints smeared by distance and motion. different instruments suggest different interpretations. The Very Large Telescope detects hints of organics. The Nordic Optical Telescope sees primarily rock. The Gemini Observatory finds ambiguity. The universe delivers its first interstellar sample in a package that resists analysis. Scientists compare Oumuamua's colours to known asteroid classes. The D-type asteroids in our outer solar system show similar reddish hues, their surfaces rich in organic compounds, but not identical. The P-type asteroids offer another comparison. Primitive bodies unchanged since formation, close but not quite. The comet nuclei studied by spacecraft missions provide additional context: dark, reddish-black surfaces created by billions of years of radiation processing, similar but distinct. Oumuamua occupies a unique position in colour space, neither purely rocky nor obviously icy, neither clearly metallic nor definitely organic. The reddish colour suggests complex chemistry. When cosmic rays strike simple molecules, they break bonds and create new ones, building increasingly complex compounds. Methane becomes, ethane becomes longer, hydrocarbons. Water ice develops hydrogen peroxide. Nitrogen combines with carbon in ways that would seem exotic in Earth laboratories. This space weathering creates a patina of processed materials, a surface layer that might hide completely different composition beneath. Only took 40,000 years of interstellar travel to paint Oumuamua in colours that reveal its journey while concealing its nature. Density estimates multiply the uncertainty. Without direct mass measurements, scientists must infer from indirect evidence. If the non-gravitational acceleration comes from outgassing, the object needs low density. If radiation pressure drives the acceleration, even lower density is required. But achieving such low densities with materials that survive interstellar journeys challenges material science. Perhaps Oumuamua resembles a cosmic pumice stone, more void than solid. Perhaps internal structures create strength without mass. Perhaps assumptions about survival requirements need revision. Some propose that Oumuamua consists primarily of water ice beneath an insulating crust. Cosmic ray bombardment would create a refractory surface layer, protecting volatile interior materials from sublimation until solar heating penetrates deeply enough. This could explain the delayed outgassing, the lack of visible coma, the unusual acceleration profile. But thermal models struggle with heat transport through such structures. The crust would need precisely tuned properties thick enough to hide outgassing, but thin enough to permit heat transfer. Nature rarely provides such convenient arrangements. The fractal dust hypothesis offers another perspective. Perhaps Oumuamua assembled from microscopic particles arranged in hierarchical structures, like cosmic snowflakes grown enormous. Such materials could achieve remarkably low densities while maintaining structural integrity through van der Waals forces and microscopic interlocking. Laboratory experiments create similar materials under specific conditions, though nothing approaching Oumuamua's scale. The galaxy might manufacture materials impossible in planetary environments, structures that require the vacuum and time of interstellar space. Metallic hydrogen emerges from theoretical extremes. Under pressures exceeding 4 million atmospheres, hydrogen transforms into a metallic state, potentially metastable at lower pressures if cooled carefully. A fragment of metallic hydrogen from a gas giant's core, ejected during planetary collision, might survive interstellar journey while maintaining exotic properties. The hypothesis pushes boundaries of known physics, requires conditions at the edge of possibility, demands accepting that nature produces materials we've barely imagined, but Oumuamua itself pushes boundaries simply by existing. Laboratory analogues provide limited guidance. Scientists create interstellar ice analogues, bombard them with particle accelerators, heat them in vacuum chambers. The experiments produce fascinating chemistry, but nothing quite matching Oumuamua's observational constraints. Each attempt to recreate possible compositions reveals new challenges. Materials that survive radiation fail thermal cycling. Structures that explain acceleration can't maintain elongated shapes. Solutions to one puzzle create new mysteries. The object seems designed to frustrate reverse engineering. The composition debate reveals deeper questions about planetary system diversity. Our solar system provides one example of how stars and planets form, one particular mixture of elements and conditions and history. Other systems might produce entirely different inventories of objects, different stellar metallicities, different disk temperatures, different migration patterns could create materials unknown in our neighbourhood. Oumuamua might be typical for its home system, but exotic here, a sample of alternative chemistry developed under foreign stars. As Oumuamua recedes, taking its secrets beyond recovery, scientists archive their spectra and hypotheses. Future interstellar visitors might confirm or contradict these tentative conclusions, or perhaps each will prove equally enigmatic, equally resistant to remote analysis, equally challenging to provincial assumptions. The universe offers samples without labels, compositions without context, materials without user manuals. Understanding requires patience measured in astronomical units and decades of departure. The tumbling never steadies, every 7.34 hours. Oumuamua completes another rotation, but not cleanly, not simply. The object wobbles through space in what dynamicists call a non-principal axis rotation state, spinning around an axis that itself rotates around another axis, like a badly thrown frisbee that refuses to stabilize, like a cosmic disaster frozen mid-catastrophe. The object carries angular momentum in the most complex configuration possible for a rigid body. This rotation state contains information about violence. Objects naturally evolve towards simple rotation around their shortest axis. The minimum energy configuration that physics prefers, internal friction, tidal forces, and collisions gradually dampen complex rotations over millions of years. For Oumuamua to maintain its tumbling state requires either recent disruption or unusual internal structure. Perhaps the same event that ejected it from its home system also set it spinning chaotically. Perhaps internal density variations prevent settling into simple rotation. Perhaps the universe preserves evidence of ancient catastrophes in the angular momentum of ejected debris. Scientists model the rotation using light curve data from multiple observatories. The brightness variations follow complex patterns, not the simple sinusoids of normal asteroid rotation. The mathematics require at least two periodic components, possibly three, superimposed in ways that suggest the object shows different faces to Earth at each rotation. The modelling remains uncertain, too few observations, too much noise, too many free parameters, but the complexity appears genuine. Oumuamua tumbles through interstellar space like a thrown stick that never stops falling. The rotation reveals structural integrity. An object hundreds of meters long but only tens of meters wide experiences significant stress during rapid tumbling. Centrifugal forces try to tear it apart. Tidal stresses from varying gravitational fields accumulate over each rotation. Yet Oumuamua maintains its shape through forces that would fragment many asteroids. This suggests material strength beyond typical space rocks, internal cohesion through molecular bonds rather than mere gravitational aggregation. Only took one tumbling interstellar visitor to demonstrate that some objects are built to last. The wobble might explain the acceleration mystery. If Oumuamua outgases primarily from specific surface regions, ancient volcanic vents, exposed ice patches, areas of particular composition, the tumbling would direct these jets in constantly changing directions. Averaged over time, the acceleration would appear to emanate from the object's centre, but instantaneously, thrust vectors would swing wildly through space. This could reduce the efficiency of acceleration, requiring more outgassing than simple models predict, potentially explaining why gas remains undetected. Attempts to determine the pole orientation face fundamental ambiguities. Without resolved images, astronomers cannot distinguish between different rotation models that produce similar light curves. The object might be tumbling end over end, or rotating like a propeller, or combining both motions in ratios that remain unconstrained. Each model implies different internal structures, different formation histories, different responses to interstellar journey stresses. The mathematics offer multiple solutions where nature presumably provided only one. The rotation period itself raises questions. 7.34 hours seems arbitrary, unconnected to resonances or round numbers that might suggest particular formation processes. In our solar system, asteroid rotation periods cluster around certain values, influenced by collisional evolution and the Yorp effect, subtle torques from asymmetric thermal radiation. But Oumuamua evolved in a different environment, under different stars, through different histories. Its rotation period carries information about processes we can only imagine. Some scientists explore whether the tumbling could be artificial, evidence of deliberate design rather than natural processes. A spacecraft might tumble to distribute solar heating, to scan different directions, to maintain stability through gyroscopic effects. But these speculations founder on parsimony. Natural explanations, however puzzling, require fewer assumptions than attributing intention to cosmic debris. The universe produces sufficient mysteries through physics alone without invoking intelligence. The damping timescale calculations yield uncomfortable numbers. For an object of Oumuamua's estimated size and density, complex rotation should decay to simple spinning within millions of years, perhaps tens of millions for extremely rigid materials. But the interstellar journey lasted longer, much longer. Either the tumbling began recently, perhaps from gravitational interaction with our Sun, or the object possesses unusual internal properties that prevent damping. Liquid cores, density variations, or extreme rigidity could extend damping timescales. But each explanation adds complexity. As Oumuamua departs, its tumbling continues unobserved. The rotation that revealed its needle shape now carries it into darkness, each turn slightly different from the last, the complex motion gradually evolving through subtle torques and internal stresses. Somewhere beyond Neptune's orbit, beyond human instruments' reach, the object still tumbles every 7.34 hours, marking time in rotations that no consciousness counts, maintaining angular momentum imparted by catastrophes whose details died with their witnessing stars. The trajectory traces backward through time like reading stellar archaeology. Where did Oumuamua originate? The calculation seems simple: reverse its velocity vector, account for stellar motions, find the intersection with a star's past position. But simplicity deceives. The galaxy rotates. Stars drift through space in complex choreographies. Gravitational perturbations accumulate over millennia. Each factor adds uncertainty to an already uncertain path. The object's home star might have died before Earth formed. Its planetary system might have dispersed into darkness. Only took trying to find one object's origin to reveal how thoroughly the galaxy erases trajectories. The velocity vector points toward the constellation Lyra, toward a patch of sky near bright Vega. But Vega sits 25 light-years away, too distant for Oumuamua to have travelled from there at its observed speed. The object would have needed 600,000 years to cross that gap, far longer than orbital reconstructions allow. Vega serves only as a directional marker, a cosmic street sign pointing toward regions unknown. The actual source lies elsewhere, hidden among dimmer stars or perhaps no longer existing at all. Astronomers construct probability clouds rather than precise origins. Within 5 light-years of Oumuamua's past trajectory lie several candidate stars. HD 2992 Force 9, a yellow star similar to our Sun. Ross 619, a red dwarf barely visible to telescopes. 2 micron survey sources identified only by catalogue numbers. Each star moved through different positions when Oumuamua might have departed. The calculations produce overlapping zones of possibility, regions where the object might have originated if ejected at particular times with particular velocities. Uncertainty multiplies with each variable. The local standard of rest provides another clue. This reference frame represents the average motion of stars in our galactic neighbourhood, the baseline against which peculiar velocities stand out. Oumuamua arrived with unusually low velocity relative to this standard, about 11 kilometers per second compared to typical stellar velocities of 20 or 30. This suggests either an old object that has gravitationally relaxed through multiple stellar encounters, or ejection from a star with similarly low peculiar velocity. The galaxy contains billions of such stars. The constraint barely constrains. Statistical arguments emerge from necessity. If Oumuamua represents typical interstellar debris, its properties should reflect common rather than rare phenomena. Most stars are red dwarfs. Most planetary systems experience dynamical instabilities. Most ejections occur during early system evolution, when planets migrate and scatter smaller bodies. The object probably emerged from ordinary processes rather than exotic events. But ordinary for the galaxy might seem extraordinary to observers familiar with only one stellar system. The age remains unknowable. Oumuamua might have wandered for millions of years or billions. Cosmic ray exposure dating, which reveals asteroid ages in our solar system, requires physical samples. Surface color provides only minimum ages, at least thousands of years for radiation reddening to develop. The tumbling state suggests relative youth, perhaps millions rather than billions of years. But these remain order of magnitude guesses. The object carries its history encrypted in properties we can observe but not fully decode. Some scientists note that Oumuamua's incoming velocity matches the motion of young stars in the solar neighborhood, particularly the Pleiades moving group. These stars formed together roughly 100 million years ago, sharing similar velocities as they disperse through the galaxy. Perhaps Oumuamua originated from a planetary system still forming, ejected during the violent early epochs when planets fight for stable orbits. The hypothesis fits the velocity data but lacks additional support. Correlation need not imply causation, even in celestial mechanics. The galactic environment through which Oumuamua travelled matters for its evolution. Interstellar space seems empty but contains magnetic fields, cosmic rays, occasional atoms, and rare dust grains. Over millions of years, these influences accumulate. Magnetic fields might induce currents in metallic components. Cosmic rays create isotopes that could reveal exposure history. Dust impacts might sandblast surfaces or deposit material. The object represents not just its origin but also its journey, a palimpsest of processes written in languages we're still learning to read. Alternative formation scenarios multiply the uncertainty. Perhaps Oumuamua formed not in a protoplanetary disk but directly from a molecular cloud, a failed star's debris, or collision ejecta from giant impacts. Each scenario implies different chemistry, different structure, different response to interstellar travel. Without knowing what we're trying to trace backward, the trajectory calculations become exercises in mathematical possibility rather than physical reconstruction. The search for Oumuamua's home becomes philosophical. Does an object ejected from its birth system still belong to that origin? After millions of years and thousands of light years, does source still matter? The atoms in Oumuamua, formed in various stars that died before our sun was born, were processed through multiple stellar generations, assembled briefly in some distant system, then scattered again into darkness. The object is simultaneously ancient and young, local and foreign, unique and typical. Its origin is everywhere and nowhere, a question the universe poses without providing sufficient information for answer. The nitrogen ice hypothesis emerges from elimination and analogy. Scientists point to Pluto, where the Sputnik Planitia Basin contains a 1,000-kilometer-wide plain of pure nitrogen ice. Solar heating causes this nitrogen to sublimate slowly, creating a thin atmosphere that refreezes elsewhere on the dwarf planet. Now imagine a collision powerful enough to excavate chunks of this nitrogen ice, to accelerate them beyond Pluto's escape velocity, beyond the Sun's gravitational grip, into interstellar space, a fragment of an exo-Pluto, wandering between stars, arriving at our doorstep as Oumuamua. The mathematics seem promising. Nitrogen ice at Oumuamua's perihelion distance would sublimate at rates potentially consistent with the observed acceleration. The sublimation would produce primarily nitrogen gas, difficult to detect with Earth-based spectroscopy, potentially explaining the absence of visible outgassing. The low molecular weight of nitrogen means less mass needs to sublimate to produce given acceleration. Every calculation nudges the hypothesis toward plausibility. Only took considering the edge cases of solar system chemistry to find materials that might explain interstellar mysteries. But creating pure nitrogen ice chunks requires specific conditions. In our solar system, nitrogen ice forms only on the coldest bodies: Pluto, Triton, perhaps some Kuiper belt objects. These worlds themselves form through complex processes involving differentiation, atmospheric cycling, and surface renewal. An exoplanetary system would need similar conditions to produce nitrogen ice plains, then suffer impacts capable of ejecting fragments while preserving their composition. The chain of requirements grows longer with each consideration. The albedo problem persists. Pure nitrogen ice reflects about 60% of incident sunlight, far brighter than Oumuamua's observed reflectivity of roughly 4%. Cosmic ray bombardment might darken the surface, creating an organic rich crust over pristine ice. But achieving such low albedo requires specific radiation doses, specific chemistry, specific preservation conditions. The object needs to be simultaneously pure enough to explain acceleration and processed enough to explain darkness. Nature rarely provides such fine-tuning without reason. Scientists model nitrogen ice erosion during interstellar travel. Cosmic rays penetrate meters deep, breaking molecular bonds, creating new compounds. Interstellar dust impacts might crater the surface or deposit material. Thermal cycling from distant stellar passages could cause fracturing. After millions of years, would recognizable nitrogen ice remain? The model suggests possible survival, but with modifications that might alter the very properties that make nitrogen ice attractive as an explanation. The solution risks destroying itself through its own requirements. The size estimates become critical. If Oumuamua consists of nitrogen ice, its mass must fall within narrow bounds. Too massive, and the observed acceleration requires impossibly high sublimation rates. Too light, and structural integrity fails. The sweet spot spans barely an order of magnitude, centered around 10 million metric tons. This corresponds to an object roughly 400 meters long by 40 meters wide. Assuming density similar to Pluto's nitrogen ice plains, the calculations work, barely, if every assumption proves correct. Fragment shape poses another challenge. Impacts that excavate planetary surfaces typically produce angular chunks, not needle-like forms. To achieve Oumuamua's extreme elongation requires special circumstances, perhaps extrusion through a narrow canyon during impact, perhaps stretching through tidal forces during ejection, perhaps preferential erosion along crystal plains during interstellar travel. Each mechanism seems possible individually. Combining them to produce observed properties requires increasingly elaborate scenarios. The nitrogen hypothesis makes testable predictions. Future interstellar objects composed of nitrogen ice should show similar properties: dark surfaces, minimal spectroscopic features, acceleration without visible outgassing. If the galaxy contains numerous disrupted exoplutos, their fragments should occasionally visit our solar system. Statistical arguments suggest one detection implies many undetected passages. Humanity might regularly receive nitrogen ice fragments from distant Kuiper belt analogues, frozen messages from worlds we'll never directly observe. Some scientists question whether nitrogen ice represents common or rare interstellar debris. Our solar system contains one Pluto with significant nitrogen ice. Extrasolar systems might contain none or dozens. The formation requirements sufficient nitrogen, appropriate temperature. Geological activity to concentrate ice might be rare or ubiquitous. Without knowing the frequency of Pluto analogues throughout the galaxy, the probability of intercepting their collision fragments remains incalculable. Oumuamua might represent the common or the exceptional. Only took one example to reveal our ignorance of galactic averages. The hypothesis survives through flexibility. When observations challenge predictions, theorists adjust parameters. Perhaps the nitrogen ice contains impurities that alter sublimation rates. Perhaps microscopic structure affects thermal properties. Perhaps surface chemistry produces unexpected albedo. Each modification preserves the core idea while accommodating new constraints. Science advances through such iterative refinement, though distinguishing refinement from rescue becomes increasingly difficult as adjustments accumulate. The nitrogen ice hypothesis balances on the edge between explanation and speculation. The hydrogen iceberg hypothesis arrives from cosmic extremes, in the coldest regions of space, where temperatures approach 3 Kelvin. Even hydrogen freezes solid. Giant molecular clouds, the stellar nurseries where stars are born, contain pockets cold enough for hydrogen ice to form. Imagine Oumuamua as a fragment of primordial ice, older than stars, a messenger from the galaxy's coldest regions. The proposal seems absurd until the calculations begin. Then absurdity transforms into remote possibility. Solid hydrogen requires temperatures below 14 Kelvin to remain stable at the pressures of interstellar space. Such cold exists only in regions shielded from starlight, deep within molecular clouds where dust grains block radiation. There, hydrogen molecules might accumulate on dust particles, growing slowly over millions of years into macroscopic ice. The process has never been observed directly. These regions lie hundreds of light years away, shrouded in opacity, but thermodynamics permits it. Chemistry allows it. Only took considering the universe's coldest natural environments to find conditions that might birth hydrogen icebergs. The properties of solid hydrogen solve several puzzles. Its density, about 1/14 that of water ice, could explain Oumuamua's acceleration with modest sublimation rates. Hydrogen sublimates at temperatures where other ices remain frozen, potentially active even in interstellar space. The sublimation produces molecular hydrogen, transparent to most observations, invisible to spectroscopy. An object of pure hydrogen ice could accelerate without producing detectable emissions. The mathematics align beautifully until practical considerations intrude. Survival becomes the critical question. Hydrogen ice is ephemeral, the most volatile solid possible. Starlight destroys it. Cosmic rays shatter its molecular bonds. Even the cosmic microwave background radiation, at 2.7 Kelvin, provides enough energy to cause slow sublimation. For a hydrogen iceberg to survive travel from a molecular cloud to our solar system requires specific trajectories, specific timing, specific luck. The models suggest possible survival paths, routes through the galaxy's coldest corridors, but the margins are thin. Gregory Laughlin and Darrell Seligman calculate the erosion rates. A hydrogen iceberg entering our solar system would lose roughly 10% of its mass to sublimation during approach and departure. Interstellar travel would claim additional mass through cosmic ray sputtering and thermal sublimation. To survive as observed, Oumuamua would need to begin its journey substantially larger, perhaps kilometers wide rather than hundreds of meters. This size evolution creates its own puzzles. How does such a fragile object maintain structural integrity while shrinking? The formation mechanism requires extraordinary circumstances. Dust grains in molecular clouds typically measure nanometers to micrometers. Growing from microscopic seeds to macroscopic icebergs demands millions of years of undisturbed accumulation. Turbulence in molecular clouds would disrupt growth. Nearby star formation would evaporate accumulated ice. The window for hydrogen iceberg formation might be vanishingly narrow, requiring quiescent conditions that rarely persist long enough. Yet the universe is vast. Even unlikely events happen somewhere. The elongated shape finds potential explanation in directional erosion. If Oumuamua spent millions of years travelling through interstellar space, cosmic rays would erode it uniformly from all directions. But during close stellar passages, including our own, asymmetric heating could cause preferential sublimation. Material facing the star would erode faster than shadowed regions. Over multiple encounters, this could carve initially round objects into elongated forms. The mechanism seems plausible until detailed modelling reveals complications. The reshaping would need to occur faster than complete evaporation, a delicate balance. Some scientists question whether hydrogen ice could maintain mechanical integrity at observed tumbling rates. The material properties of solid hydrogen at relevant temperatures remain poorly constrained. Laboratory experiments struggle to recreate interstellar conditions. Would hydrogen ice fracture under rotation? Would thermal gradients cause structural failure? Would cosmic ray damage accumulate into catastrophic weakness? Each question lacks definitive answers. The hypothesis rests on extrapolations from limited data. The hydrogen iceberg model makes specific predictions about future interstellar objects. If molecular clouds regularly produce and eject hydrogen ice fragments, some should arrive at our solar system with measurable hydrogen sublimation. Advanced spectroscopy might detect absorption features as sublimated gas passes between the object and Earth. The objects should show acceleration profiles distinct from conventional comets, activity at larger solar distances where water ice remains frozen. Time will test these predictions, though hydrogen ice visitors might be rare enough that decades pass between examples. The philosophical implications run deep. If Oumuamua consists of primordial hydrogen ice, it predates our solar system by billions of years. It formed before the Sun, before Earth, before the molecular cloud that birthed our stellar neighbourhood. We would be examining matter from the galaxy's early epochs, preserved in the only form that could survive such ages, the simplest possible molecule in the coldest possible state. A cosmic time capsule written in hydrogen, delivering messages about conditions we can never directly observe. Only took one mysterious visitor to suggest connections between our solar system and the galaxy's ancient past. The light sail hypothesis emerges from Abraham Loeb's calculations at Harvard. If Oumuamua has sufficiently low mass per unit area, less than 1 gram per square centimetre, then solar radiation pressure alone could produce the observed acceleration. No outgassing needed. No exotic ice is required. Just an object thin enough that photons push it like wind fills a sail. The mathematics are straightforward. The implications are not. For Oumuamua to be a light sail, it would need to be less than 1 millimetre thick across its entire 400-metre length. Nature doesn't build such structures. The thinnest geological formations measure metres. The most delicate ice sheets span centimetres. To achieve millimetre thickness at hundreds of metres scale requires either technological construction or physics unknown to planetary formation. The hypothesis divides scientists between those who find it absurd and those who find it merely improbable. The universe has surprised us before, but extraordinary claims require extraordinary evidence, and Oumuamua provides only ordinary mysteries wrapped in incomplete data. The radiation pressure calculations account for Oumuamua's changing distance from the Sun. Photon momentum decreases with the inverse square of distance, matching the observed acceleration profile. The force depends on the object's reflectivity and cross-sectional area. For typical asteroid albedos around 10%, achieving sufficient acceleration requires extreme thinness. The object would resemble aluminum foil scaled to football field dimensions. Every photon impact would transfer momentum, gradually pushing Oumuamua away from the Sun like countless microscopic collisions. If artificial, what purpose would such a structure serve? Interstellar light sails could propel spacecraft between stars, riding stellar winds across cosmic distances. But Oumuamua tumbles chaotically, which would neutralize any navigational purpose. It arrives from no particular star and heads toward no particular destination. If technology, it appears to be broken technology, derelict debris rather than active probe. The galaxy might contain the wreckage of ancient civilizations, their light sails drifting like abandoned boats, their makers long extinct or evolved beyond physical exploration. Critics point to formation challenges even for artificial origin. Manufacturing millimetre-thin sheets hundreds of meters wide requires advanced materials and construction techniques. Launching such delicate structures would risk destruction. Surviving millions of years of cosmic ray bombardment seems impossible for such thin material. Microscopic impacts would perforate any sail. Thermal cycling would cause fatigue fractures. The hypothesis requires not just technology, but miraculous preservation. Only took considering artificial origin to reveal how even advanced civilizations face engineering limits. Natural analogues exist at smaller scales. Graphene sheets 1 atom thick, mica that cleaves into transparent films, ice crystals that grow as hexagonal plates. But scaling these to Oumuamua's dimensions while maintaining structural integrity challenges materials science. Perhaps unknown processes in protoplanetary disks could create vast thin sheets through accretion or condensation. Perhaps tidal forces could stretch and flatten initially compact objects. Perhaps electromagnetic fields in space could organize matter into planar configurations. Each natural mechanism seems more contrived than simply accepting that thin objects shouldn't exist at such scales. The tumbling motion argues against the light sail interpretation. Functional sails would stabilize perpendicular to radiation pressure, maximizing thrust. Oumuamua's chaotic rotation would average out acceleration vectors, reducing efficiency, unless the tumbling itself serves a purpose distributing thermal loads, scanning different directions, confusing observers. But these speculations pile assumptions upon assumptions. Occam's razor, already strained, threatens to shatter under accumulated complexity. Some propose Oumuamua represents a natural membrane, like a cosmic bubble wall. In certain theoretical scenarios, phase transitions in space could create thin boundaries between regions of different vacuum states. Dark matter interactions might produce sheet-like structures invisible, except through gravitational effects. Cosmic strings could leave planar wakes as they move through matter. These ideas venture beyond established physics into realms where mathematics permits possibilities that may never manifest in reality. The light sail hypothesis makes testable predictions. Future interstellar objects with similar acceleration profiles should show evidence of extreme thinness occultations, revealing translucency, rotation patterns suggesting minimal moment of inertia, spectroscopy indicating unusual composition. If the galaxy contains populations of natural or artificial light sails, statistical arguments suggest more should arrive. Each detection would constrain formation mechanisms and survival probabilities. Time and observation will arbitrate between natural and artificial explanations. The debate reveals science at its most uncertain. When data underdetermines models, when observations permit multiple interpretations, when conventional explanations strain credibility, even unlikely possibilities enter consideration. Oumuamua forces confrontation with our assumptions about what the universe builds and preserves. Whether natural or artificial, its properties push boundaries. The object departed, taking its true nature beyond recovery, leaving only questions that multiply faster than answers arrive. Sometimes the universe's teaching method involves presenting puzzles without solutions. The explanations proliferate like bacterial cultures in warm media. Each scientific paper proposes new mechanisms, new compositions, new formation scenarios. Oumuamua might be a fractal aggregate of dust particles, a shard of exoplanetary crust, a cosmic dust bunny grown enormous, solidified comet exhaust, a fragment of a disrupted super-Earth, interstellar smog condensed into solid form. The hypotheses multiply because the constraints permit multiple solutions. The universe delivered a puzzle with too many missing pieces for unique reconstruction. The porosity models explore structural possibilities. Perhaps Oumuamua resembles a cosmic foam, more empty space than solid material. Laboratory experiments create aerogels with densities approaching that of air while maintaining structural rigidity. Scaled to astronomical sizes, such materials could achieve the low mass-to-area ratios needed for radiation pressure acceleration. But creating porosity at 100-meter scales requires processes unknown in planetary formation. Accretion typically compacts materials. Gravity opposes voids. Only took imagining Oumuamua as cosmic Swiss cheese to reveal our ignorance about large-scale structure formation. Amorphous carbon emerges as another candidate. When carbon-rich materials undergo cosmic ray bombardment, they can transform into complex networks of carbon atoms arranged in disordered patterns. This material might be both lightweight and strong, capable of surviving interstellar journeys while maintaining elongated shapes. The carbon would appear dark, matching Oumuamua's low albedo. Sublimation of trace volatiles trapped within carbon matrices could produce acceleration without visible outgassing. The hypothesis seems plausible until quantitative modelling reveals mismatches with observed properties. The polymer hypothesis invokes radiation chemistry. Cosmic rays striking simple molecules can trigger polymerization, creating long-chain compounds that didn't exist initially. Over millions of years, this process could transform primitive ices into complex materials with properties unlike anything in our solar system. These polymers might have unusual thermal properties, sublimating at unexpected temperatures, producing gases transparent to our instruments. The chemistry becomes increasingly exotic as theorists attempt to match observations. Each adjustment preserves possibility while straining credulity. Some propose Oumuamua consists of materials typically destroyed before observation. Perhaps it contained abundant water ice that sublimated just before discovery, leaving behind a refractory skeleton. Perhaps it underwent phase transition during solar approach, transforming from one material state to another. Perhaps humanity observed it during a brief transitional period when its properties temporarily defied categorization. These scenarios require remarkable timing arriving just as unusual processes occurred. The universe rarely provides such convenient coincidences. The exotic ice zoo expands continuously. Carbon monoxide ice, methane clathrates, ammonia hydrates. Each material has specific sublimation temperatures, specific spectroscopic signatures, specific formation requirements. Theorists combine them in various ratios, searching for mixtures that match Oumuamua's properties. The parameter space becomes vast composition, structure, formation history, thermal evolution. With enough free variables, almost any observation can be explained. But explanations that require fine-tuning often indicate missing understanding rather than captured truth. Differential sublimation models add temporal complexity. Perhaps Oumuamua's composition varied with depth. Like geological strata recording different epochs, solar heating would expose successive layers, each with different properties. The acceleration profile might reflect changing composition as sublimation proceeded. This could explain why simple models fail. They assume homogeneity where none exists. But confirming such models requires observations we lack. The object departed before humanity could observe complete thermal cycles. The primordial planetesimal hypothesis reaches toward his solar system beginnings. Perhaps Oumuamua represents material that never underwent planetary processing, preserved since protoplanetary disk epochs. Such objects might retain primitive compositions, unmodified by differentiation or geological activity. They would carry information about conditions during planetary system formation, frozen records of ancient chemistry. But surviving billions of years without modification challenges preservation mechanisms. Time destroys information through entropy's patient persistence. Magnetic field interactions provide another acceleration mechanism. If Oumuamua contains conductive materials or magnetic minerals, interaction with the solar wind's magnetic field could produce forces. The object's tumbling would create time-varying magnetic signatures, possibly inducing currents that interact with ambient fields. The acceleration would depend on composition, structure, and magnetic history in ways difficult to predict. The hypothesis adds electromagnetic complexity to an already overcomplicated puzzle. Only took considering every possible force to realize how many phenomena we can't remotely measure. The multiplication of hypotheses reflects healthy science confronting insufficient data. Each proposal makes predictions, suggests observations, advances understanding, even if ultimately wrong. The process resembles evolution ideas compete for explanatory fitness. Successful concepts spawn variants. Failed hypotheses face extinction. Through this conceptual natural selection, science approaches truth asymptotically. Oumuamua catalyzed theoretical creativity that advances regardless of which specific hypothesis proves correct. Sometimes the journey toward understanding matters more than reaching destination. The explanations will multiply until another interstellar object arrives, providing new constraints, confirming or eliminating hypotheses. Or perhaps each visitor will prove equally mysterious, each requiring unique explanations, each revealing how provincial our understanding remains. The galaxy might manufacture objects through processes we haven't imagined, in environments we've never simulated, from materials we've never synthesized. Oumuamua's gift isn't answers, but better questions. The naming happens faster than understanding. Within days of confirming Oumuamua's interstellar origin, the International Astronomical Union faces a classification crisis. Their naming conventions, refined over centuries, assume objects belong to our solar system. Comets receive letters and numbers based on discovery date. Asteroids get numerical designations after orbital confirmation. But this object follows no orbit, belongs to no established category, represents something entirely new. The bureaucracy of cosmic nomenclature scrambles to accommodate a visitor that respects no borders. The committee creates a new designation system overnight, the letter I for interstellar, followed by a number indicating order of discovery. 1I, the first confirmed interstellar object. The classification seems simple until considering its implications. This single character represents humanity's acknowledgement that our solar system isn't isolated, that objects routinely cross between stars, that we've joined a galactic community we barely comprehend. A new catalogue begins with one entry, waiting for siblings that might arrive tomorrow or might not appear for decades. The name Oumuamua comes later, suggested by the Pan-STARRS team that discovered it. In Hawaiian, the word carries multiple meanings: scout, messenger, reaching out for a first distant messenger. The name requires special characters, an okina marking the glottal stop that most keyboards can't type. Scientists worldwide struggle with pronunciation, with typography, with explaining to colleagues why this object deserves a name rather than just a number. Only took one interstellar visitor to reveal the linguistic challenges of cosmic diversity. The rush to classify reflects human need for categories, for boundaries, for definitions that separate this from that. But Oumuamua resists classification beyond its trajectory. Is it an asteroid? It shows no volatile activity. A comet? It lacks the defining tail. A new category entirely. The taxonomists debate while the object recedes, indifferent to human filing systems. Nature provides phenomena. Humans impose categories. Sometimes the two refuse to align. The media coverage explodes faster than scientific understanding develops. Headlines proclaim alien spacecraft, interstellar probes, messages from distant civilizations. The scientists' careful uncertainties transform into sensational certainties through successive retellings. Each iteration adds speculation presented as fact. The object becomes a Rorschach test for human hopes and fears about cosmic loneliness. Those seeking aliens find evidence of technology. Those preferring natural explanations find exotic chemistry. The same data supports contradictory narratives depending on preceding assumptions. Professional astronomers find themselves explaining statistics to reporters, uncertainty to politicians, scientific method to Twitter. The public wants answers: is it aliens or not? Science offers probabilities, confidence intervals, null hypotheses. The gap between scientific and public discourse widens with each press release. How do you explain that extraordinary claims require extraordinary evidence when ordinary evidence is all we have? How do you convey that we don't know represents honest assessment rather than failure? The betting pools emerge within hours. Scientists wager coffee, beer. Publication authorships on Oumuamua's nature, nitrogen ice versus hydrogen ice, natural versus artificial. The bets represent not serious belief but acknowledgement of uncertainty, playful engagement with cosmic mystery. The wagering continues long after Oumuamua passes beyond observation. Some bets designed to remain unresolvable, permanent reminders of temporary ignorance. Patent applications appear for Oumuamua-inspired technologies, light sails based on theoretical interpretations, radiation shields mimicking hypothesized properties, propulsion systems assuming artificial origin. The patents reference scientific papers selectively, cherry-picking supportive statements while ignoring caveats. Innovation accelerates based on speculation about an object we barely observed. Human imagination fills gaps that data leaves empty. Only took one mysterious visitor to spawn an industry of maybe. The naming committee prepares for future discoveries. If one eye exists, two eye must follow eventually. They draft protocols for naming interstellar objects from different cultures, different observatories, different nations. Should each discovery team choose names from their local language? Should names follow themes like mythology or exploration? Should artificial objects, if confirmed, receive different designations? The bureaucracy prepares for possibilities that might never manifest or might arrive tomorrow. The cultural impact ripples outward. Musicians compose symphonies inspired by Oumuamua's trajectory. Artists paint interpretations of its hypothesized appearance. Science fiction writers incorporate interstellar visitors into narratives. The object enters humanity's collective consciousness not as what it is still unknown, but as what it represents first proof that things come here from elsewhere. The classification transcends taxonomy, becomes philosophical. We are not alone in receiving cosmic debris. Years after departure, Oumuamua retains its provisional designation. The one eye that seemed temporary becomes permanent through usage. The classification system created for one object waits for expansion. Perhaps two eye will arrive tomorrow, or next year, or next century. Perhaps it already passed while we looked elsewhere. The universe doesn't schedule its revelations for human convenience. The catalogue of interstellar objects remains a monument to patience, one entry waiting for companions. The detection reveals more about our blindness than our vision. Oumuamua passed within 24 million kilometers of Earth, closer than Venus, yet humanity noticed only after it began departing. The object crossed Earth's orbit twice, approached the Sun closer than Mercury, spent months within telescope range. But automated surveys looked elsewhere. Human attention focused on other targets. The first confirmed interstellar visitor nearly came and went entirely unobserved. Only took one lucky detection to reveal how many we must have missed. Pan-stars. The telescope that spotted Oumuamua surveys merely 1/40th of the sky each night. Its primary mission involves finding potentially hazardous asteroids, not interstellar visitors. The detection happened by accident, a consequence of looking for something else entirely. If Oumuamua had passed through a different region of sky, if its trajectory had angled slightly differently, if clouds had covered Hawaii that October night, humanity would never have known. The universe delivered a cosmic messenger that we almost fail to notice. The calculations of missed objects prove sobering. If interstellar visitors arrive at rates implied by Oumuamua's detection, thousands have passed through our solar system during human history. While ancient astronomers mapped constellations, interstellar objects crossed Earth's orbit unobserved. While Galileo pointed his telescope at Jupiter, visitors from other stars passed closer than Mars. While modern surveys photographed millions of asteroids, interstellar travellers slipped through gaps in coverage. We've been receiving cosmic mail for millennia without checking the mailbox. Current surveys can detect objects like Oumuamua only within small volumes of space. The inverse square law governing brightness means detection capability drops rapidly with distance. An object visible at 1 astronomical unit becomes invisible at 10. The observable volume represents a tiny fraction of the solar system's extent. Most interstellar visitors likely pass through outer regions where no telescope can spot them. They arrive, loop around the Sun, and depart. Their passage is recorded only in gravitational perturbations too subtle to measure. The Vera Rubin Observatory, under construction in Chile, promises improvements. Its 8-meter mirror and 3-gigapixel camera will survey the entire visible sky every few nights. Scientists estimate it could detect dozens of interstellar objects annually, perhaps hundreds if they're more common than conservative estimates suggest. The observatory will transform Oumuamua from singular discovery to prototype, from exception to example. But even this powerful instrument has limits. Smaller objects, darker objects, faster objects will still escape detection. The response time problem persists regardless of detection capability. Oumuamua travelled at 26 kilometers per second, crossing astronomical units in days. By the time astronomers confirmed its interstellar nature, it had already passed its most observable positions. Detailed study requires weeks of planning, scheduling, coordination. The objects don't wait. They follow hyperbolic trajectories that offer one chance for observation. Miss the window and the opportunity vanishes forever. Only took trying to study one interstellar visitor to reveal how poorly our observation infrastructure handles transient phenomena. Some propose dedicated interstellar object surveys, arrays of small telescopes continuously monitoring high-probability arrival zones, artificial intelligence systems trained to recognize hyperbolic orbits in real time, rapid response protocols that immediately redirect major observatories toward new discoveries. The proposals require funding that competes with other priorities. How much should humanity invest in catching glimpses of cosmic passers-by? The question has no obvious answer. The missed science haunts astronomers. If detected earlier, Oumuamua could have been studied during approach, observed through perihelion, tracked with multiple instruments simultaneously. Spectroscopy could have sampled different surface regions as it tumbled. Radio observations might have detected molecular emissions. Spacecraft might have been redirected for close encounters. Instead, humanity caught only the departure, like arriving at a train station as the last car disappears around a bend. Future missions consider interstellar intercepts. Spacecraft parked at gravitational balance points, ready to chase newly discovered visitors. Ion drives capable of matching hyperbolic velocities. Miniature probes that could be launched quickly toward passing objects. The engineering challenges multiply with examination. Intercepting objects moving at interstellar velocities requires capabilities beyond current technology. We can observe visitors but not visit them. The universe provides samples we can see but not touch. The psychological impact of improved detection might prove significant. If dozens of interstellar objects appear annually in survey data, their mystery might diminish through familiarity. Or perhaps each will prove unique, expanding rather than resolving puzzles. The galaxy might send diverse messengers, ice mountains, metal shards, objects that defy every category. Improved detection capability means confronting rather than ignoring cosmic diversity. Sometimes ignorance feels more comfortable than incomplete knowledge. Oumuamua taught us to look differently. Surveys now include algorithms specifically searching for hyperbolic orbits. Astronomers developed rapid response protocols for unusual objects. The community learned that interstellar visitors require different observation strategies than solar system residents. The next Oumuamua might be detected earlier, studied longer, understood better, or it might prove equally mysterious despite improved preparation. The universe tests our observation capabilities with moving targets that don't return for second chances. Already, Oumuamua races beyond human reach, beyond radio contact, beyond the most powerful telescopes humanity can build. 5 years after discovery, it passes Neptune's orbit. 10 years out, it crosses the heliopause where solar wind meets interstellar medium. A century from now, it will be a light day distant. A millennium hence, 10 light days. The object that briefly visited our consciousness returns to the anonymous darkness between stars, carrying its secrets beyond any possibility of retrieval. The universe gave us 45 days of observation, then nothing, forever. The trajectory extends into futures humanity won't witness. In 40,000 years, Oumuamua will approach another star, passing perhaps as close as it passed our sun, perhaps triggering detection by whatever intelligence might exist there, or perhaps it will drift through empty systems, witnessed only by automatic surveys, classified by alien bureaucracies with their own designation systems. The object becomes a thought experiment in cosmic archaeology evidence that exists but can't be examined. Knowledge that visited but didn't stay. Scientists archive every photon collected from Oumuamua, every spectrum, every brightness measurement. The data occupies mere gigabytes, a tiny fraction of one hard drive. The sum total of humanity's direct knowledge about our first confirmed interstellar visitor. Future astronomers will analyze and reanalyze these observations, applying new techniques, new theories, new understanding, but no new data will arrive. The data set is complete, frozen, finite. We have what we have. Only took one interstellar object to teach us about opportunities that don't repeat. The theoretical papers continue multiplying. Each month brings new hypotheses, new calculations, new interpretations of the same limited observations. The literature on Oumuamua already exceeds 1,000 publications, more words written about it than photons collected from it. The disparity will only grow. Centuries from now, scholars might still debate its nature, constructing elaborate theories around 45 days of incomplete data. Human curiosity extends beyond observation's reach. The next interstellar object might arrive tomorrow, or might already be approaching, still too faint for detection, carrying different mysteries or confirming existing hypotheses. The galaxy presumably contains quintillions of such objects, each potentially visiting our solar system once before disappearing forever. The sample size will grow slowly, each detection adding constraints, eliminating possibilities, expanding questions. But Oumuamua will always be first, the prototype against which others are measured, the discovery that opened a new window. Children born after 2017 grow up in a universe where interstellar visitors are confirmed reality, rather than theoretical possibility. The knowledge seems ordinary to them, unremarkable, obvious. Of course objects travel between stars. Of course we occasionally detect them. Of course most pass unnoticed. The profound becomes mundane through familiarity. Only those who remember the before times appreciate the discontinuity, the moment when humanity's cosmic perspective shifted permanently. The cultural memory will outlast scientific interest. Oumuamua entered our language, our art, our collective imagination. The word appears in crossword puzzles, trivia games, science fiction stories. People who can't explain its significance still recognize its name. The object achieved immortality not through its properties still unknown, but through its timing. First confirmed interstellar visitor. The qualification matters. There were surely others before, unseen, unconfirmed. There will be others after, better observed, better understood. But Oumuamua owns firstness forever, somewhere beyond Neptune, beyond Pluto, beyond the Kuiper Belt. Oumuamua tumbles onward. Every 7.34 hours, it completes another rotation that no one observes. Its acceleration has ceased. The sun's influence negligible at such distances. It coasts on momentum earned during perihelion passage, neither speeding up nor slowing down, following a straight line through curved space-time. The object returns to the state it maintained for millions of years before entering our solar system alone. Dark, silent, the universe continues delivering mysteries faster than humanity solves them. Dark matter, dark energy, fast radio bursts, now interstellar visitors. Each discovery reveals not answers but the depth of our ignorance, We're cosmic infants, just beginning to perceive phenomena that have operated since before Earth formed. Oumuamua represents not conclusion but commencement, not answer but question, not ending but beginning. The first confirmed interstellar object is already gone, but the era it inaugurated has just begun. Time flows forward, Earth rotates, the sun spirals through the galaxy. Oumuamua recedes at 26 kilometers per second, its path diverging from ours along dimensions spatial and temporal. The distance between us expands faster than light could traverse in human lifetimes. The object we barely glimpsed, barely understood, barely had time to wonder about, has already passed beyond recovery. Connection lasted 45 days out of 13 billion years. The universe specializes in brevity framed by eternity. Only took one interstellar visitor to remind us that most of existence happens elsewhere, elsewhen, beyond observation's finite reach. Oumuamua is already gone, forever. The numbers dissolve into darkness now. 26 kilometers per second becomes just motion through void. 7.34 hours becomes rhythm without witness. The calculations fade. The hypotheses quiet. The debates settle into silence. Oumuamua continues its ancient journey, indifferent to the brief moment when consciousness noticed its passage. Space returns to what it mostly is, emptiness punctuated by rare events. The solar system resumes its patient orbit around the galactic center. Other objects surely pass through, undetected, unremarked, carrying their own mysteries from star systems we'll never visit. The cosmos operates on timescales that dwarf human awareness. We caught one glimpse, one fragment, one passing shadow that refused to explain itself. The observatories continue their surveys tonight. Automated systems scan the sky. Computers analyze trajectories. Somewhere, perhaps, another interstellar visitor approaches, still too faint to detect, carrying information about places we can only imagine. Or perhaps the space between stars remains empty for now, holding only the usual cosmic debris, the familiar asteroids and comets that belong here. Stars drift slowly overhead. The universe expands. Galaxies recede from each other along vectors we'll never follow, and somewhere in that vastness, Oumuamua tumbles onward, neither mission nor message, neither probe nor projectile, just matter following physics through dimensions of space and time that permit no return. The first confirmed interstellar object has become memory, data archived, mystery preserved, story without ending. Sleep finds us all eventually, like darkness between stars, like the quiet that fills observatories at dawn. Rest now. The universe continues its patient revelations tomorrow and tomorrow and tomorrow.